So we start graphing this function by finding the zeros. Oh, thank you. But by finding the zeros, we just have to know the factors. And oh, look, it's already in factored form here. So the zeros for this particular function are what? What are the zeros? X equal to, what does this first factor tell me that a 0 is? 2, with a multiplicity of what? 2, which means does it bounce or does it cross? Bounce. So it does not cross the x-axis. The second 0 is x equal to -3. What's that one's multiplicity? 1, which means it's going to cross the x-axis there. And what's the third 0? 5. What's its multiplicity? 1, which means it's also going to cross. Odd multiplicities cross, even multiplicities will not cross or will bounce. What is the degree of that polynomial? 4, so it's an even. And what is the leading coefficient? Is it greater than or less than 0? Since all of the first terms are positive and there's no negative in the very front, so it's going to be a positive leading coefficient. And if we were to calculate, the end behavior then for an even positive function is like an even or a quadratic that's positive, which means it's going to be both up at the end. And just to make a really good graph, we could also have the y-intercept by plugging in a 0, which would be 0 minus 2, so that's -2 squared, 0 plus 3, that's 3, and 0 minus 5, which is -5. Multiply all of those things together, we should get -60. Because that's 4 times 3 times -5, that's -60. Great. Again, this is just kind of reviewing what we've done before. This tells us that we have zeros where the graph crosses at 2, 5, and at -3. So I'm going to cross the x-axis or touch the x-axis at -3, at 2, and at 5. I also know that my end behavior should be both upwards because that's the degree and the leading coefficient. So if I were to graph this, I would start at the end behavior and go through the first 0. Oh, I forgot to graph my y-intercept. Here's -60. I cross through the 0 of -3 because it has a multiplicity of 1. I get to -60 and I go to the next critical point, which is the 0 of 2. Can I cross through 2? No, we said the multiplicity was 2, which means it's going to bounce, which means it'll come back down. But then it'll cross the x-axis at 5, since it has a multiplicity of 1, meeting up with my other end behavior on the other side. That's what we did before. That was graphing just regular polynomials. That's where it's equal to 0. However, we're going to be dealing with inequalities. So not only can we graph them, we can also find out where polynomial functions are positive, where they are negative, or where they are exactly 0. So to solve where f of x is greater than or equal to 0, you're just going to find the values of x that make f of x positive or show up above the x-axis. To find out where f of x is less than 0, that means negative, you're just going to find out what makes it negative or when it is below the x-axis. And what we did last time or before when we were solving them, that's when it's just set exactly equal to 0 or when it's crossing or touching the x-axis. So our job today is to look at graphs, sometimes we'll do it algebraically, and be able to discuss when the graph is above 0, below 0, or equal to 0. Really pretty simple. If I were to annotate this graph for where it's above 0, all I'm looking for is the parts of this graph that are literally above the x-axis. Do you see that there's 2 sections here where it's above the x-axis? That would be the solution to that inequality. If I was looking for where it was below the x-axis, like I'd literally just be looking for all of these points because that's where it's below the x-axis or less than 0. Equal to, is just the points where it's literally equal to, touching, or crossing the x-axis. The challenging part about this is writing the answers in the correct notation because it's all interval notation, where I'm going to request that we use interval notation. So using the graph that we have above, so you have this graph on your paper, we're going to answer these questions. Now, this is all the equation that we graphed. Don't fret here, you already have this graphed. So this part A is just asking to find the values of x where the graph is purely above the x-axis. Greater than is above. So if we look at the graph, we just need to write down the sections where it's above the x-axis, so the green sections. That means that this is going from -infinity to 3, but not including 3. Picking up back up at, sorry, not 3, -3. Picking back up at 5 and going off to infinity. Why did I choose to use parentheses here and not brackets? What do you mean by not touching? Because I think you're on the right track. It's not equal to. At -3, the graph is exactly equal to 0. That's not asking for equal to, it's just asking for greater. So in which case, when I switch the question and now I'm asking for greater and equal to, see how there's now the line underneath it? So we want two colors now. We want both the green and the blue section because we want where it's greater and it's equal to. Don't get ahead of me though, because you might answer this incorrectly, and I know a lot of you are writing in pen. For this one, we would answer the following, and I want you to explain to me why this is like this. We'd go -infinity to -3 and 2 and from 5 to infinity. Whoa. Why? What's happening here? Remember, the question is, where is it greater than or equal to? Including every place it's equal to. So if I look at my graph, obviously this is where it's above, so it's greater. It's equal to it right there, so I include the bracket this time to include the point of 3. And if I keep going along my x-axis, when's the next time it's equal to 3? Equal to 0. At 2, but it never gets bigger than 0, it's just equal to it. So I have to include the point 2, or the x value of 2 in my equal to part, and then I pick it back up at 5 and go off to infinity. So we can't forget about the individual points where it's equal to, even if they're not a part of a bigger interval. Does that make sense?
So is it like basically just combining?
Yeah. We're combining all three sections. There's 3 parts where this is either greater than or equal to. One of the parts just happens to be a single point. Because right here, it's still equal to it, but there's nothing other than the exact number 2, because it's equal to it right there. Okay? Kind of tricky, because it's details in the symbols that really get you. These end up being squiggly brackets because it's just a set of one number, so those should be squiggly brackets instead of the square brackets, because it's a set of one numbers. Okay, if we see a few more examples, maybe it'll start to clear it up. I know I'm kind of going off screen here. The next question here, question C, wants to know where that graph is less than 0, but only less than 0. So only the red parts, not the blue parts, which means it's going from -3 to 2. I pick up my pencil at 2 because it's equal to it right there. I don't want equal. I pick it right back up, and I go all the way to 5. Do we follow that one? We have 2 intervals where it's less than 0, here and here, broken up by the equal to part. And then something interesting happens for part D. Part D wants to know where it's less than and equal to. So we can include the blue parts. So I want to write the answer. I want you to tell me why this is the correct answer. The correct interval where it's less than or equal to is from -3 to 5. Now, why is that? Why did I have to do so much extra on B when I didn't have to do that much extra on D? Like on B, I had to include a whole like extra coordinate point, but on D, I didn't have to do that. Why?
Because 2 is bouncing off 0.
Yeah, that's exactly right. If remember, I'm looking for either blue or red on this one. My blue starts here, and then I get to red stuff, blue stuff, that's okay, red stuff, blue stuff, and then it all stops. This entire interval, it is either less than or equal to it. I didn't have to pick up my pencil technically because I'm allowed to be equal to on that one. So this point isn't a point of discontinuity in that domain because it goes from here to here for either red or blue, red and blue. Part E is a simple equation. We want to know where it is exactly equal to 0. There are 3 points we found where it is equal to 0, so we just put them in a set. The 3 points that it's equal to 0 are at -3, at 2, and at 5. There's my set of numbers where it is exactly equal to 0. And I'll scoot it up because I know some of you can't see behind people's heads. So doing the intervals themselves, like seeing where it's above, below, not all that difficult, but getting the notation correct is probably the hardest part of these. If you think you got it and you're good to go, we have, I think it's either 2 or 3 chances on the back page. Is it 2 or is it 3? 3 chances for us to practice. I want you to honestly to just try them now. The best thing you would do for me to get started is color on the graphs. So if we colored the first one, everywhere it's exactly equal to 0, I would put blue. Everywhere it's above 0, I would put green. And anywhere it's below 0, I would be putting red. I don't know what your color scheme is, but that's mine. But then I'm going to stop talking. I want you guys to try to figure these out. You can do all 3 if you can. I know I'm cutting off some of your thinking, but we'll try 1. That way, in case you didn't have it, you can try like number 2. You can try 3 and 4. So if this is my graph, and again, for part A, I only want where it's greater than 0. That means I only want from 0 to 1, and then from 2 to infinity. Because that's where the green part is. But the moment it changes to be greater than or equal to, I can include the blue parts because I can include where it's exactly equal to, which means this only changes to being from 0 to 1 with brackets because of the equal to, and a bracket around the 2 as well for the equal to. We didn't have to have an extra little setting or a set for a particular number because all of the equal to numbers were included in the other intervals. For less than 0, we just want the spots where it's less than, so that's from -infinity to 0, and then from 1 to 2. All parentheses because none of them are exactly equal to it because we just want when it's less. But when we can go equal to, we should have from -infinity to, what was that number, 0 with a bracket. And then 1 to 2, but this time with brackets. Because we can be exactly equal to the x-axis. And then E, the numbers where it's exactly equal to, should be the set of numbers 0, 1, and 2. Because that's exactly where it's equal to 0. I guess I didn't color code this. Questions? Does that clear up some if some of us were stuck? Keep going on 3 or 4 if you haven't answered those. Here's what we should have, bless you, should have gotten for A, B, C, D, and E for example 3. I'll give you a second to look at it. If you have questions, now's a great time to ask.
How is it?
If you read the graph, that's a great question. So this is a rational function, and if you think about rational functions, they all have vertical asymptotes. This one happens to have 2 vertical asymptotes appearing at -1 and 1. So there's breaks in my graphs at those particular values. So I read the graph to figure out where it started and stopped, bounded by those vertical asymptotes. Some of us are done with example 4, so I'm going to keep going. I know not everybody is, but we'll talk through this one. So For example 4, I see I have all of this that's below and above and equal to, so we can answer the same questions. Again, noticing where it's above, below, and equal, not that hard, but writing the notation, kind of difficult. So first we want where it's just above, which is at 1, 2, 3, this is -4 to 0. Then I have to pick up my pencil because I can't include equal to yet. But then from 0 to infinity, still positive. When I get to include the equal to part, though, I don't have to pick up my pencil at 0, and I can just go from -4 to infinity. Because I don't have that break since I can be exactly equal to 0. All of that is either exactly equal to or above the x-axis, all of this. For below, there's just one section. It's from -infinity to that -4. And when I can include being equal to 0, it's still from -infinity to -4, but I close the bracket. And I can't forget about the one other little piece that is exactly equal to 0. And then last but not least, where it is equal to 0 is at -4 and 0. So don't forget about those little extra pieces that are not included in the larger interval where it is equal to 0 on those less than equal to or greater than or equal to's. So answering by a graph, fine and dandy. But not all the time I'm going to let you use a graph to answer these. We still need to be able to do it algebraically. So we're going to kind of pull a few more things together that we've learned about before to be able to solve them using a sign chart. Oh, the things from the pre-chapter that we hated the most because everybody skipped it on the quiz. It's back. Great. We're going to solve the polynomial inequalities using a sign chart. Now, I've done this one on your paper, but it didn't print in color, obviously. So I colored in the number line and then realized it would be all just like, printer color. So if you want to color yours the way I have mine colored, that would be ideal. I realized that after I printed them. I was like, come on, ding dong. All right. So for this one, we wanted to know where this polynomial was greater than 0. Not equal to, greater than. So when I solve the polynomial to find my critical numbers, I'm setting it not equal to 0. If there were a line underneath that symbol, you would say equal to because we're allowed to be equal to 0. But we don't want it to be equal to 0, so we're going to say not equal to 0. We factor. We use the zero product property to solve. Does this all look familiar to you? We find the solutions, and we're able to graph it on a number line. -3, 0. Those are my critical points. It creates 3 subintervals for me that I need to test using signs to decide if it's positive or if it's negative. So I come over here and I pick a number in the first subinterval. I picked -10 because it's very obviously in that first subinterval. If I plug -10 in here, that's going to be a negative number squared. If I plug -10 in here, that's going to be -10 plus 3. That's still a negative number. So I have a negative number squared times a negative number. What's a negative times a negative? Positive. And positive times negative is? Negative. So that section of the polynomial will be below the x-axis. I don't know what it looks like because you're not graphing it, but that section is less than 0. The second section I plugged in -1 because it's in the interval. You could plug in -2 or -0.5 if you really want to. But if you plug in -1, you'd end up with a negative number squared times a positive. Negative times negative is positive. Positive times positive is positive. So it's green. That section would be above. Do the same thing for the third section. You plug in a number using a sign chart to decide what the sign would be, either positive, which is above, or negative, which is below. And then we think back, what was this question actually asking? This question was asking, where is it above the x-axis only? Not equal to, just above. So I only want the green sections, not including the blue ones, which is from -3 to 0 and from 0 to infinity. Do we kind of see how this works? Can we do one together? Great, let's do number B together. Oh, look, it's already factored for us. Isn't that nice? Since it's already factored for us, we can go immediately to what the solutions should be. Now, question, do I write equal to 0 or not equal to 0 for this one? Equal, because we have the little line underneath the symbol right here. That means we can be exactly equal to 0. The blue parts count. So I know that x minus 2 could be equal to 0. x minus 3 squared could be equal to 0, and x minus 8 could be equal to 0. So my solutions, or my critical points, are at 2, at 3, and at 8. Fabulous. Those are the numbers I put on my number line, making sure, in this case, they are in number order, but if they're not, that you actually put them in number order. Do I put opened or closed circles on those critical numbers? Close. I'm going to make mine blue because that's the color scheme I've been using. Those are exactly equal to 0. How many subintervals did I create on this number line? 4. That means I have to test 4 different numbers. Okay, the first, second, third, and fourth subinterval I'm going to test the following way. For the first subinterval, what's a number that's easy to use that's less than 2? Even easier. 0, way easier to use. You can use whatever number, it would work. 0 is just very easy to use. If I were to plug in a 0, air quotes on the word plug in, 0 minus 2, that's a negative number. 0 minus 3, that's a negative number, but I'm going to square it. And 0 minus 8, that's a negative number. All right, I have negative times negative squared times a negative. Can we keep track of all of that? It ends up being positive. Negative squared is positive, so you have negative times negative, which is positive. So that subinterval would be green because it's positive. What's a number in the second subinterval I could use? Between 2 and 3. 2.5. You could use 2.1. You could use 2.4. I'm going to use 2.5. If I plug in 2.5, 2.5 minus 2, that's a positive number. 2.5 minus 3, that's a negative number that we will square. And 2.5 minus 8, super negative. What's a positive times a negative squared times a negative? Negative. So that section will be below the x-axis. Or for me, I would color that little section red. What's a number in the third subinterval I can use? 5. That's a pretty easy number to use. Great. 5 minus 2, that's a positive number. 5 minus 3, that's still positive, but we're going to square it. And 5 minus 8, that's negative. We have a positive times a positive squared times a negative. Also negative. So that means I'm going to color it red. What's a number in the fourth subinterval I can use? That's what I would use. 10 minus 2 is a positive number. 10 minus 3 is a positive number that we will square. And 10 minus 8 is a positive number. So positive times positive squared times positive, positive. So now that we've done all this work, what was the original question even asking? Remember, we want to know where this graph is greater than or equal to 0. So the two colors I'm including in my final answer are going to be the green sections and the blue sections, which means my answer should be from negative infinity to 2 with a bracket, because it's equal to, the number 3, and the interval from 8 to infinity. What are your questions, because you're about to try one on your own? For those of you stuck on this last one, I'm going to start putting my work up on the board, but don't look until you're ready. Okay, so here's what it should have looked like. Take a look up at the board, see how you did. Your numbers you plugged in the purple part can be different as long as they are in the correct interval, like they're actually in between the two numbers. But we should have found that since the actual question here was asking where is it less than or equal to, we're answering with both the red and the blue parts where the graph is below and equal to the x-axis. This one didn't require an extra little section or set for a particular number because all 3 of my zeros or places where it crosses the x-axis, we're included in the like larger interval part. Questions, comments, concerns? That's polynomials. We've been dealing with polynomials for a minute. And so the next step in this is to take what we know how to do of this with the interval stuff and how to write our final answers and apply it for not polynomial functions, but rational functions. So when you've got it all written down, flip this, I guess we're on to the third page here. I've done the first example for you, and I'm lingering on this page because I see some people still writing. But we can do the same thing with rational functions. So if we want to solve the rational inequality using a sign chart, we eventually will get to the sign chart stuff, but what we need to remember is what to do with numerators and denominators. First things first, we're going to make a note to ourselves here. Denominators are always equal to 0, or not equal to 0, because if you have a denominator that is 0, you have a vertical asymptote. So bad, because it's a break in the graph. The numerator is going to depend on the sign as to whether you say it's equal to or not equal to 0. So for the numerator, you're either going to have these two symbols, which means that you are looking for the numerator to be not equal to 0, or you will have a numerator or any of the signs with the equal to part. That's when you're going to want to include equals to. That didn't explain that quite right, but let's say you have these two symbols. That's when you set the numerator equal to 0, not equal to 0. It's a lot of repeated words. Does that make sense? If the numerator, or if the question is asking you either greater than or less than, don't make the numerator equal to 0. If the question is asking you for it to be equal to 0 in either direction, you're going to make it equal to 0. Is that clearer? I think. Hopefully I didn't confuse you. So on this one, we have two parts to solve. We need to solve both the numerator and the denominator for its respective zeros, either equal to 0 or not equal to 0. So for this first one that I did for you, I noticed that the symbol was just less than. So I set the numerator not equal to 0 and solved for what solves the numerator. I then found out what the denominator cannot be equal to. So I have these two critical numbers that go on my number line. Ta-da. I have 3 intervals, 1, 2, 3, and I do the sign chart for the intervals. This time, though, it's a rational function. So I have a numerator over denominator, but it works the same as multiplication. What's a negative divided by a negative? A positive. What's a positive divided by a negative? Okay, so we can still do the sign chart thing. We're just plugging it into numerators and denominators. Then we can answer the question, because it asks me only where it's less than 0, which is here in the red part, not including negative 9, all the way to 5. Can we do one together? We will probably only have time for one of them. So I want to show you the second one, actually. So we're going to skip B just so we have time. B is on the notes that I posted online, so if you want to go fill that part in, you can. You're not missing anything important with B, but we need to do C. Because C has some issues with it. Compared to the other ones we'd been using, what do you notice this one is set equal to? Ooh, that's a problem. We need it to be 0. That's fine. You can subtract numbers from side to side, right, to make it 0. So this would end up being 3x minus 5 over x plus 2 minus a big 2 less than or equal to 0. I can do that. That's just general math, moving it from side to side of an inequality. But now here's my problem. Can I actually subtract a fraction with the denominator of x plus 2 and a fraction with the denominator of 1? No, this is going to go, not no solution. It's going to go back to the lesson we just did, where we need to have them have a common denominator. What should be the common denominator here? X plus 2. Okay, so if I have x plus 2 on this side, that's good. I don't have to change the first one. But the second one, I need to multiply by x plus 2 in both top and bottom, so it has a common denominator. And now I can ignore the denominators and deal with only the numerators. This is going to be 3x minus 5 minus 2x minus 4, distributing the negative 2 less than or equal to 0. So if I combine all of that, 3x minus 2x, that's just x, and negative 5 minus 4, that's negative 9. We need to solve this numerator that can be equal to 0. Why can this numerator be equal to 0 when the numerator in number 1 had to not be equal to 0? The sign of this problem has the equal to part, so we can make the numerator equal to 0. Great, which means x can be equal to 9. Fabulous. This is my numerator. It's equal to because the original question has an equal to symbol. I'll look on A, it was just less than. This is less than equal to. So the numerator can be equal to 0. But then I have to know what my denominator cannot be equal to. What can my denominator not be equal to? Negative 2, because we know that x plus 2 can't equal 0, so x can't be negative 2. That's coming from my denominator. So we deal with the numerator, either equal to 0 or not equal to 0. We deal with the denominator always not equal to 0. And then we can make our number line with those two critical numbers of negative 2 and 9 and do our subintervals. Now, as a note, the thing that I'm going to plug into this time for ease is going to be the simplified numerator, which was x minus 9, and then the denominator, x plus 2. That's what I'm going to plug this stuff into. In the first interval, what number can we plug in there?
0. Negative 1. I mean, negative 5.
Negative 5, negative 10. I'm going to do negative 10 because that's what I did on my notes. Negative 5 works. Use negative 5 if you'd like. So negative 10 minus 9, that's a negative number. Negative 10 plus 2, that's still negative, which means that section is going to be positive. Ooh, I forgot something important. I forgot to circle my numbers. Do I put an open or a closed circle on negative 2? On negative 2? Negative 2 cannot be equal to x, so we're going to put an open circle there. How about a open or closed on 9? That one is closed for sure. Good job. Okay. In my second interval, what number can I plug in there? 5 works. What's easier? 0. 5 totally works. Use 5. There's nothing wrong with using 5. We're trying to save time here. 0 minus 9 is a negative number. 0 plus 2, that's a positive number. Negative divided by positive is a negative, which means that little section will be less than 0. In the third subinterval, what's an easy number I can use? 10 is in that interval. We can use it. 10 minus 9, still positive. 10 plus 2, definitely positive, which means that little section is back to being positive. So to answer the actual question, we go back to the symbol. The symbol says that we are looking for where the graph is less than or equal to 2, or less than or equal to 0 once we solved it for 0, which means I want to include negative 2 all the way to 9 in my solution. I guess I could have colored that 9 blue so it was a little bit better. So the rational functions are treated just the same as polynomials. You just sometimes have to remember a few extra things. Like if it's not set equal to 0, and this goes for polynomials too, you have to set it to 0 first. Okay, numerators are numerators, denominators can never be equal to 0. Those are things you have to remember.